Hello everybody, welcome to Bayesian A/B testing video in the large-scale machine learning section of ML Expert. In the last video, we talked about A/B testing and how there's often a control group and one or more treatment groups, and the idea is to determine if the treatment group is better, the same, or worse than the control group. The frequentist approach like to use p-values and things like that. However, the Bayesian approach is different. Now, the experimental setup is the exact same as we saw in the frequentist A/B testing, except the way that we're interpreting the results is going to be different. So here, Bayesian, you can imagine that we're going to be using Bayes' rule in some way, and this is Bayes' rule. You may recall this from the machine learning crash course. The idea is that we want to know the probability of some hypothesis being true given some data. This will be our posterior. The likelihood is going to be the probability of some data given our hypothesis, and then this is going to be the prior of our hypothesis. The denominator here will expand out to this to explore all of the different hypotheses that we have. In this case, we have the null hypothesis, which means that the control and the treatment groups are the same. We also have the alternative hypothesis, which means that the treatment and the control groups are different. To actually solve for this value, we'll go ahead and need to plug in the terms here. So this is going to be equal to that. This is going to be equal to that. This is a beta distribution. It's not hugely important that you're intimately familiar with all of these terms here. The main thing to take away from this equation is that the posterior and the prior are both going to be of the same type of distribution. That means that if we plug in all those substitutions that we have before, this posterior comes out to be this distribution here. So this is just a beta distribution with some alpha and beta priors. And then to get the final distribution, we add the number of clicks in our click-through probability, and we increment the number of sends for how many ever sent push notifications that we have sent out. So for me, it generally helps to visualize these things instead of just the math alone. The beta distribution is going to represent a distribution over the click-through probabilities. So here we need our prior. Our prior is going to be a beta distribution. The alpha and the beta being a 1 means that we have an uninformed prior. That means that our prior assumption is that the click-through probability can take on any value of equal probability between 0 and 1. The posterior is going to be that beta distribution we saw earlier in the video. And these are going to be the number of successes and how many trials total, which will create the posterior distribution. Let's say that we sent out 2 push notifications, and one of those push notifications was clicked, the other one was ignored. Here, our prior distribution isn't going to change. However, the posterior distribution did change. Intuitively, I would say that the click-through probability of our push notifications is 50%. This is because half of the push notifications that we sent out resulted in someone clicking on it. And we can actually see that here with this posterior distribution. The peak is going to be right at 0.5. So that's exactly what this means. The only thing that the posterior distribution includes is the probability distribution around 0.5 itself. So it's saying that 0.5 is most likely. It could also take on these values, and these values, it's just less likely to do so. Let's say that we've sent out 10 push notifications now, and 2 of them were clicked. In this case, I would assume that our click-through probability is 20%. But since we're using a beta distribution here in the Bayesian methodology, that is true for the most likely value of the click-through probability, but there's also this beta distribution around that click-through probability. So here, the value of the click-through probability taking on a 40% value is a lot more likely than it taking on a 60% value. As more push notifications are sent out, and as more people either click or don't click on these push notifications, the distribution has less variance around the value of its peak. So here the peak is at 7%, and now we know that it's almost 0% chance that the click-through probability is 40%. So here, if we've sent out 1,000 push notifications and only 70 users clicked on it, that's still 7%, so that's where the peak is. And here we see the variance shrink even more around that 7%. This will continue along through the entire experiment. So this would happen for the control group, and let's say these were the results of the treatment, so 80 people clicked, so we had the distribution move over slightly to the right. If one group has 7%, that would be here, out of 1,000 trials, and the other group had 80 out of 1,000, then the Bayesian approach is to compare those distributions and not just the single numbers that we got for the frequentist approach. So in the Bayesian approach, we want to know the probability of B being greater than A. And in this case, we would examine the beta distribution produced by group B and the beta distribution produced by group A. How we do that is we sample from A and B's posterior, that's the distribution that we just saw, and we get the percent of the times that B is greater than A. So let's say we sampled the A distribution 1,000 times and the B distribution 1,000 times. If B was truly 8 at its peak, you're more likely to get higher values from that distribution. So in general, that will increase the probability that B is greater than A. Another thing that we want to look at when we're considering Bayesian A/B testing is the loss between the two groups. So let's say that we ended up choosing B over A, even though B was actually worse than A. How would this be possible? Well, remember when we were looking at the distributions, Group A distribution had its peak at 7, and Group's B distribution had its peak at 8. However, there was a small overlap here, and that small overlap means that there's a chance that we could actually pick B but get A's results. So what we really want is to sample the differences between A and B, and that will give us the loss from choosing B over A in the case that B is actually worse. So with that loss, we can multiply that by the probability that A is greater than B, and that would give us the expected loss. This will be in the same units as our metric. In this case, it was click-through probability. As an example, let's assume B is greater than A. If it's really not, when we think it is, then our loss will be equal to the probability that A is greater than B times the differences between A and B. And these are just sampled. So we would have a whole bunch of these, and every single time we would subtract A from B and take the max of that and 0, since we're just concerned with the loss. So if it's actually a gain, we don't want to count it. Now, another thing that we could do is look at the expected gain. So let's assume that B is greater than A, and if it really is, then our expected gain is going to be equal to the probability that B is greater than A multiplied by the differences between B and A. And again, we're going to take the maximum between the differences and 0, since we're only concerned with the gain and not the loss. Alright, so as we're carrying on this experiment, how do we know when to stop? If the expected loss is less than some threshold that we don't care about, then we can stop. What this means is that as the experiment goes on, and let's assume that the two groups are in fact different, then the expected loss will shrink. This is because the two distributions are getting further and further apart, and the variance surrounding those distributions is growing thinner and thinner. So even if you do make a mistake and launch the wrong one, the probability of that happening grows smaller and smaller and smaller. This threshold should be something that you're comfortable with losing. Now remember, even though that there is an expected loss, you'll also have a significant expected gain to compare against that expected loss. So why would you pick Bayesian A/B testing over frequentist? Well, generally it's easier to interpret the results. If I tell you p-value is 0.05 and the confidence interval is this, that could mean something to you, but more often than not, I would just like to know what's the probability that the experience B is better than the experience A. And here we can answer that question directly. Also, there's often fewer samples that we have to collect to reach a launch decision. This means faster experiments and faster improvements. Now, one of the tools, in addition to all the tools that we talked about in the previous frequentist A/B testing, is Visual Web Optimizer. Alright, so in this video we went over why Bayesian A/B testing is sometimes preferred over frequentist A/B testing. We went over how to interpret the results of a Bayesian A/B test, and also the tools that you can use to help you perform Bayesian A/B tests. That wraps up this Bayesian A/B testing video in the large-scale machine learning section of ML Expert. Thanks for joining, and we'll see you next time.